When a progress bar fills a screen, or a database query returns thousands of rows in milliseconds, we witness the output of high-speed sequential execution. These programming constructs are not arbitrary syntax. Every loop, every memory allocation, and every recursive function is a direct implementation of discrete sequences. This reveals the concept of complexity as sequence growth. To predict whether a piece of software will function under pressure, you must understand exactly how the sequences inside its architecture scale. Optimization occurs when a developer identifies the specific mathematical sequence governing an algorithm and swaps it for a pattern that scales more efficiently. To navigate this, we consult a master taxonomy, a map that categorizes every major algorithm and operation down to its specific discrete math foundation. This blueprint outlines the distinct mathematical patterns that dictate the physical limits of computation and memory. The structure is built on three core pillars: arithmetic for linear growth, geometric for exponential scaling, and factorial for combinatorial calculations. Before a developer can predict if an algorithm will succeed under heavy load, they must first precisely locate its underlying logic within these three domains. We begin with the most common pattern in programming, the arithmetic sequence. This formula defines a sequence where each term increases by a constant amount. We denote that constant difference as d, which is added sequentially to our starting value, a1. In code, this maps directly to for loops, stepping forward by 1, I equals 0, 1, 2. It controls memory allocation and pagination logic. Look at the summation formula. S sub n equals n times a1 plus an divided by 2. This equation allows developers to calculate the total of a linear series in constant time. Instead of forcing the processor to iterate through every single item in the sequence, the formula computes the total instantly. Because arithmetic sequences offer perfectly predictable, stable linear growth, they serve as the reliable workhorse for routine iterations and standard memory tasks. When logic moves from addition to multiplication, we enter the domain of geometric sequences. Here, growth is driven by multiplying each term by a constant factor, the common ratio, r. The value of any given term is a1 multiplied by r to the power of n minus 1. This multiplicative math drives rapid scaling and networking retries, bit-shifting memory, and binary trees, where each level doubles. To track total volume, use the compounding sum formula. S sub n equals a1 times r to the n minus 1 divided by r minus 1. That compounding calculation governs complex scaling algorithms and is the core math used to model viral spread in analytics. Geometric sequences create a critical trade-off. They make binary searches incredibly efficient by continuously dividing datasets, but they can also trigger catastrophic memory failures if a process multiplies unchecked. To process these sequence datasets mathematically, we rely on two primary aggregators, sigma and pi notation. Sigma is the additive aggregator. It executes formulas that sum a sequence of terms, represented as the sum of a sub j from j equals m up to n. In practice, sigma maps directly to array reduce operations and SQL sum queries used to total costs and statistical means in analytics. Next to it is pi, the multiplicative aggregator. Instead of adding, it calculates the continuous product of a sequence. On the left, sigma stacks data linearly. On the right, pi notation handles operations multiplying across dimensions, like calculating compound probability grids and matrix determinants. There is a specific algorithmic edge case for pi known as the empty product. If the lower bound m is strictly greater than the upper bound un, the product resolves to 1. This rule prevents cascading zero multiplication errors from wiping out calculations in code. While standard sequences build the raw data structures, sigma and pi act as the computational engines, reducing massive data streams into singular, actionable metrics. Finally, we reach the most extreme growth pattern in computation, the factorial. Denoted by n!, a factorial is the product of all whole numbers from n down to 1. Crucially, for recursive base cases, the factorial of 0 is defined as 1. Factorials apply directly to permutation ordering. 3 data packets yield 6 possible arrangements. 4 packets create 24. By 10 packets, the number of arrangements explodes to over 3.6 million. This explosive growth is triggered by scheduling problems and route-finding algorithms, where the system attempts to calculate every possible path to find the most efficient route. Factorials represent the combinatorial wall. They mark the exact threshold where brute force computing becomes physically impossible, mandating intelligent algorithm design to bypass the mathematical bottleneck. When we evaluate these mathematical structures in a live environment, the practical limits of software architecture become clear. This answers why an algorithm that functions in local testing with 10 users can completely crash a production server at 1,000 users. Visualizing these sequence rules on a chart of operations versus data size reveals big O notation. The shallow linear curve represents arithmetic logic, O of n. The steep curve is geometric, O of 2 to the n. The vertical spike is factorial, O of n factorial. Big O analysis is the study of these specific mathematical sequences as the data size, n, approaches infinity. Mastering arithmetic, geometric, and factorial sequences is the vital prerequisite for analyzing complexity, optimizing loops, and engineering software architecture that survives real-world scale.